So coming to the present scenario of agriculture, you can see almost 349 million people across 79 countries are still facing acute food insecurity. Food insecurity only. It is not the food availability I am telling. It is food insecurity. It can be either affordability crisis or it can be even the availability crisis. And it was only 287 million population during 2021. This is the like coming to water. Why our water is so precious? Water is the basic necessity of life. From the school days we are listening, the basic necessities of life. Water, air, clothing, shelter, so many things, the food, like that. Water, maybe it comes first immediately after our oxygen or air. And it is essential for all our life, that is even in our day-to-day activities, it is an essential component. And when you think about the availability of water, is it a scarce resource? Do you think it is a scarce resource? Because the entire earth is having almost more than 90% of water surrounded by oceans. Lot of water is there all around us, but still the availability of fresh water is very, very meager. So we don't need the salt water from ocean, but we need the fresh water for all our life activities. That is why water is so precious in that way. So you can see in this statistics, oceans that take almost 96% of water, and only the fresh water that portion is only 2.5%. And even in that 2.5% of fresh water, you can see 68% is in the form of ice, glaciers, etc. And another 30% water is underground, groundwater resource. And the surface water which is readily available is hardly 1 or 1.2%. And in that 1.2% also, that is the surface water available, you can see again 69% is just like ice caps. Then lakes hold around 20% of fresh water. The atmosphere is having almost 3% of water. Atmosphere is taking water. Then our living things, including human beings, all the living things, plants, they hold only 0.26, very, very minute quantity of fresh water. And our rivers take almost 0.5% of water, then another 2.56, 2.6% is in the swampy or marshy areas. And our soil also holds some moisture, which is almost 4% or 3.8%. So that is the distribution of water in earth. And you must have heard about the Sustainable Development Goals. No, there are 17 goals, and in that the 6th goal is regarding water, clean water and sanitation. That is the 6th point of Sustainable Development Goal. Under 6.4.2, there is mention about water stress. So, stress. Just you can see the definition here. Water stress means it is the ratio of the fresh water withdrawn by the total resources. The ratio of the freshwater withdrawal by the total water resources, that is called water stress. And in many regions, many countries, they are having this stress value varying. You can see the world stress value, water stress value is almost 18%. In Asia, it is Southeast Asia, Eastern Asia, like that, it is coming to 21-46% like that. And the maximum stress is in Africa. Northern Africa, you see more than 100% stress. That means a very, very acute shortage of fresh water for all the life activities. And the European countries is almost without any stress. So coming to the role of water in agriculture. So agriculture is the sector which takes the maximum quantity of fresh water. Almost 70% of our freshwater withdrawal is by farming, our sector. And 16% is taken away by our industrial sector and 12% by our. Then coming to water footprint, you must have heard about the carbon footprint. Carbon footprint. You know what it is? Anyone can answer carbon footprint or water footprint? Water footprint means it is the sum total of the water taken away or consumed or appropriated for the formation of a product or a process starting from the beginning up to its end. Starting from the beginning up to the end product, how much water it is appropriating, that fresh water it is, that a particular process or a product is taking, that is called water footprint throughout its entire life period of time. That is water footprint. And it can include both the direct drawing of water as well as the indirect uses of water. And the first, it was coined by that Hoekstra and Hung during 2002. This concept, water footprint, it was termed by Hoekstra and Hung. Actually, they are based on a lot of literature is available by these two persons. And Wageningen University based from the database from 1995 to 2006 database, they have worked out the water footprint of many of the crops, including cereals, even some of the tuber crops, then pulses, so many products. They actually so many crops they have already worked out based on the database available during this period, 1995 to 2006. And there is also another word called virtual water. Virtual water is nothing but a hidden water. So we may not be seeing that water component inside a particular product or a process, but it is hidden. So it is just like a water footprint only. So usually the unit of water footprint is cubic meter per ton or cubic meter per year. When you consider a crop production, say example rice production, this many tons, that means the unit will be cubic meter of water per ton of rice or cubic meter of water per ton of wheat or whatever it is. Any crop product it will be expressed in terms of cubic meter per ton. Or for a particular area, maybe for example Indian, suppose if we work out the water footprint, average water footprint of Indian population or a particular region or a particular population, it will be expressed in terms of cubic meter per year. Per year, how much water we are taking, we are consuming, like that it is. So just you can, now I will present some of the examples of the water footprint values. Suppose if we are taking 1 cup of coffee, how much is the water footprint? 1 cup of coffee, if I am preparing, how much is the water footprint for a cup of coffee or tea? 1 cup of water, is it not? So 1 cup of water we will be taking, adding sugar, coffee powder, everything, and we are preparing 1 cup of coffee. But when you think in terms of water footprint, we should not think from the coffee powder. Coffee powder, from where it is coming? Coffee bean, the coffee, what is that, plantation. From the beginning, if you work out the coffee plantation, its harvesting, bean production, bean processing, up to making a cup of coffee, it takes almost 140 liters of water to make a cup of coffee. 140 liters, you see the difference. A cup of coffee means hardly we pay 15, Maxima airport we will pay some 100 rupees or 200 rupees. But in terms of water, if you are working out the value in terms of water, means it is almost 2,800 rupees. Because it needs 140 liters of water to prepare a cup of tea, a cup of coffee. Here I am showing some more examples of the water footprint of some of the common products available around us. See, 1 kg of chocolate. Chocolate, it needs sugar, it needs the cocoa butter, like that. So many raw materials are required for preparing the chocolate. So before that, so the virtual water consumption behind all the production of all these raw materials also we have to take into account while working out the water footprint. So 1 kg of chocolate means almost 17,196 liters of water it takes. Similarly, 1 kg of beef, 15,000 liters, 1 kg of butter, again the cow, the livestock value, everything we have to take into account. Then the bread, ultimately from where it is coming from, that wheat flour. So again it takes water for the wheat, the whole production of wheat, it's harvesting, processing, powdering, flour making, everything. And again the 1 kg of apple. So like that, whatever we see with our eyes is not the actual water consumption by a particular product or a process. There is some hidden water or virtual water which also should be taken into account while working out the water footprint. So here actually this is again I told based on the data based from the Wageningen University, they have worked out the average water consumption or water footprint of different nations. USA 2,842 cubic meter per year average. That means one person is consuming almost 2,842 cubic meter of water per year. But in India, it is little less only. We are fortunate, at least 1,089 is our water footprint, closely followed by China. So these are the water footprints of different nations. Just you can see the USA, China, India, like that. It is in terms of giga cubic meter per year. When you work out the water footprint of a nation means it includes both the imported water footprint as well as the exported water footprint. Suppose if from India we are exporting some cotton, for example, if we are exporting cotton or sugar products, some of the products if we are exporting means some of the water consumed from our nation is going out to some other nation. Is it not? So for that nation it is a income, just like a receipt of water. And whatever, and for us, like India, for exporting countries, it is a loss of water from that exporting countries. That is just like a vice versa. When we are importing some of the products from outside, we are getting water from that corner, and for that country, that exporting country, it will be a minus. Then coming to again for the water footprint. Actually, there are three components. The water footprint means there are three components. One is the green water footprint, then we have the blue water footprint, and we have the grey water footprint. So, green water footprint is nothing but the water we are receiving from the precipitation. Precipitation means what is precipitation? Rainfall, the nice fall, like that, the precipitation. Naturally, what we are getting from the nature, that is precipitation, and it can be stored either in the root zone, or it can be taken up by the plant, or it can be transpired like that. Then, coming to the blue water footprint, from one source, whatever available naturally is our green water footprint. What is available from a water source? For example, a groundwater resource or a borewell means from that we are taking some water and irrigating to some other source. Some other plants, if we are irrigating to another 1 hectare area, that particular water, it may not come back to that original source. It is nothing but the irrigation. Whatever quantity of water we are taking from one source and applying to another source. That is irrigation. So blue water footprint means the irrigation component of agriculture. Then there is another term called grey water footprint. Grey means because of our not only agriculture, industrial or whatever it is, there are chances of polluting our water sources. For example, some pesticide or some fertilizer, leaching loss of these nutrients or some pesticide pollution or the industrial pollution. If some of the water bodies are polluted, we should have the responsibility to get it back to its normal condition. So whatever the quantity of water required to bring back the water source standards to the original level or to an acceptable level. For that also we need water. That means the quantity of water to reduce or to ameliorate the pollution level of a water body. That is called grey water component of water footprint. So there are, like that, there are three components: green, blue and grey water. And how will you assess the grey water footprint? There are two main approaches for assessing the water footprint, like the volumetric approach that is again given by the Hofstra et al. In 2011. They have worked out some formulae to work out the water footprint, blue, grey and green. And we also have another approach, life cycle analysis approach by the LCA community. And the common or the most common method to assess the water footprint is our volumetric approach coined by Hofstra et al. 2011. Even we can assess the water footprint at three levels: level A, level B and level C. For example, level A means that whatever assessment or based on the literature just earlier I told, there are some values assessed already for the different crops. It is based on a broad database in the sense 1995 to 2006. So with that, covering most of the countries, almost at the global level, if we are assessing means the accuracy will be less. Is it not? If you are assessing at the world level means naturally the accuracy will be less. It is the level A method of or the level A approach of working out the water footprint. When you come down to a national level or a regional level of water assessment, for example, throughout the globe, water footprint assessment for rice production, if we are assessing, it will be around some 1,200 cubic meter per ton. For example, I am telling. But when you come to Asia, how much is the water footprint of rice? In Asia means it may be only 900 or 950 cubic meter per ton. These are all examples only I am telling. And again, if we are coming down to a smaller area like Kerala or Tamil Nadu, for a smaller area, even in Coimbatore, if you are assessing, if you have the data to assess the water footprint of rice, it may be some more with the accuracy you will get the data as maybe 870 cubic meter per ton. That means level C. You are coming down to a very, very smaller level. Throughout the globe it is level A assessment. Then when you come down to a regional or a national level, it will be like level B. Then level C means still you have to come down to a smaller area with the accurate data. So the accuracy will be more and the data will be more reliable. So coming to crop production, that means any crop production, rice, wheat or tuber crops like cassava or pulse crop, millets, sugarcane, like that. Any crop you take, these are some of the steps involved in the water footprint analysis. Actually, I told already, it is actually a combination of blue, green, and grey water footprints. So, when you, how will you work out the green component of water footprint? The CWE means that is crop water use divided by the green component. CWE divided by the yield component. That means, suppose that means it is green means nothing but the precipitation. Suppose if you are getting 500 mm of rainfall during a particular season, so 500 mm, that 500 mm as such may not be available to the crop. So you must have heard about the effective rainfall. Is it not? The effective precipitation. So we have to convert that rainfall into effective rainfall, and then you divide that effective rainfall by the yield of that crop. Then you will get the water footprint green assessment. Then coming to the irrigation aspect, that the crop water use blue. Maybe above this 500 mm, we will be irrigating the crop for another 300 mm if we are irrigating for a particular season. So 300 mm we will take divided by the yield, whatever harvesting yield we are getting, that part will be taken as the water footprint blue component. And again the grey component means this is the calculation. Alpha means the runoff factor. Then the applied chemicals, some herbicide, what is the quantity of chemicals if we are adding for a particular crop production, that if it is polluted your water source, we have to clean that water source to its original level. So the C max means the maximum polluted level, maximum applicable, minus the natural level of pollutant at the time of our withdrawal divided by the yield. That means we have to compensate the or we have to ameliorate. We have to apply more water to that water source to bring it back to its normal acceptable level of pollution. So that is the component of grey water component. So by adding these three, that water footprint green, blue and grey, we get the final total water footprint of a particular crop product. Then again for a process means, suppose sugarcane production, then the various steps involved in production of sugar. So every step it involves the consumption of water. So step by step you have to add and come out with a final figure. Step by step you can add, stepwise accumulative approach is there, or from the beginning to the end product we will take the water consumption at a stretch. So that is the two chain summation approach and the stepwise accumulation approach. Then even we can calculate the water footprint for our energy levels also. For example, heat energy or electricity, bioethanol or biodiesel, like that. So for all that assessment, what we need is the water footprint, the water quantity of water taken away by that crop divided by the energy content of that crop, heat content or electricity content of that crop, then the bioethanol content of that crop or biodiesel component of that crop. And it will be expressed in terms of volume by energy. Here's some more. Then coming to the root and tuber crops in which I am working. Actually, cassava, have you seen some of the tuber crops like cassava, then sweet potato is already there, then elephant foot yam. So we are working on some almost 10 crops, cassava, sweet potato, then yams, 3 kinds of yams we have, then the elephant foot yam, then taro, 2 types, that small taro and xanthosoma, that is there, then Chinese potato is there, then arrowroot is there. So some of the crops are already available in this campus also through our ACRP on tuber crops. So so just you can see the area cultivated under tuber crops. Africa is having the maximum acreage under root and tuber crops, followed by Asia. But when you compare the area cultivated for cereals, Africa only half of this one. The cereal cultivation is Africa is only half, and the maximum area is in Asia when you are taking the cereal cultivation. And some of the root and tuber crops, Hofstra and Hung, they have already worked out the figures based on the database available already. And the potato almost 225 cubic meter per ton. Then yams means that kachil. Then sweet potato 383 and cassava 564, and taro is a very moisture sensitive crop. It needs more water. Taro mostly it is cultivated under lowland conditions with regular irrigation, so the water footprint also will be naturally high for our taro, some of the tuber crops. And under our CTCRI condition, the cassava variety, that is in cassava also we have the short duration variety and the normal duration variety. Short duration means it needs only 6 months. The normal duration variety means it needs 10 months to harvest. Cassava crop, you must have, you know that cassava crop. 6 months varieties are there, then 10 months varieties are also there. So this crop under irrigation, especially under drip irrigation, furrow irrigation, and we have made a comparison. Even under rain-fed condition, the water footprint values is very much less compared to the reported figures. You can see the water footprint for under drip irrigation, it is coming only 53 to 102, and furrow irrigation 259, and the rain-fed crop is 109. The main reason is in a CTCRI, we have used only a short duration variety of 6 months. 10 months crop means more water it needs. More duration means naturally the crop will take more water. That is one thing. And another thing with respect to cassava is, regarding cassava productivity, India ranks first, almost 35 tons per hectare, compared to the world average, which is only some 10, 12 or 13 tons per hectare. The world average yield of cassava is very, very less compared to the Indian average. And the Asian average also is high. And we have very high yielding input. Improved varieties of cassava with a less duration, and again under drip irrigation, definitely the water consumption of the crop will be very, very less, but at the same time we have the varieties which gives you 60 tons or more than 60 or 80 tons, like that. So many most of our recently released high yielding varieties, they are giving you more than 60 tons per hectare. So either we should increase the yield level or we should decrease the water consumption by a crop. That is the only possibility, or that means the sustainable water management is the only strategy to reduce the water footprint. So here you can see a comparison of tuber crops water footprint versus the cereals. So the left side you can see maize, barley, rice, then sorghum, millets, etc. There the total water footprint you can see. Everywhere it is more than 100, more than 1000 or 1200. But compare that when you take the water footprint of our tuber crops, it is less than 600. So that means almost 3 times water, or 2 times or 3 times water it requires to produce cereals when you compare it with our tuber crops. But the tuber crops are also starch-rich, energy-rich crops. So this is the bioenergy, the comparison. It is the water footprint of making the bioenergy from tuber crops as well as from other here potato. You can see the total water footprint of potato in terms of ethanol, and cassava almost 125. The value is less compared to the other rice. Paddy needs 191 cubic meter per ton of ethanol production. Similarly, per liter of ethanol production also, it is in terms of energy as well as in terms of ethanol production. You can see potato 2399 cubic meter per ton of ethanol, while the cassava value is only 2926. And the rice, everything is, but sugarcane is much less. Only regarding water consumption, the sugar beet, the sugarcane, etc., they stand first when compared to the tuber crops. Here again the water footprint in terms of electricity, you can see some of the crops like potato, cassava, it is displayed here, and compared to sugar beet, maize, sugarcane, barley, the water consumption is less compared to potato and cassava. It is that means the potato and cassava they are not good raw materials for producing electricity. We have some other crops which gives you more electricity from less water, like sugar beet, maize, sugarcane, like that. So these are in general about, and just we have initiated our studies only in water footprint, and we have to have water footprint of all our tuber crops under different growing conditions, and that is our main objective now, and we will be working on it. So our main the purpose is either we have to increase the water use efficiency, or we have to decrease the water footprint in agriculture. That is, being the researchers or the students in the field of agriculture, our objective is either to increase the water use efficiency or to decrease the water footprint. Both are inverse. The relation is inverse. So water, so we are very fortunate to live in a condition where water is not that costly. We are with 10 or 20 rupees, we are getting a bottle of fresh water. But in future, the situation may not be like that, and we should have the responsibility to hand over our freshwater resources to our next generation also. So that is just like a thought-provoking speech only. I did this one. We have not done much on tuberculosis. So based on the data that literature collected, we have published also in Environment Development and Sustainability one paper also I could publish. Just a beginning only, actually, on this topic. I am also a beginner only. So so thank you for your patient listening. And I think at least you got some idea about the importance of water and what is water footprint, and like that you got some rough idea at least. And if you have any queries or
we are doing import and export based on water footprint.
How it is affecting the water footprint?
Actually, we are doing import and export based on water footprint.
No, we are not importing or exporting in terms of water footprint. No, we are not at all cared about the water consumption if we are importing 2 tons of sugar to another country. We are not at all bothering about the water footprint. But virtually, our water is going out. Now, whatever water is consumed by the crop or up to that processing level, naturally it consumes some water. But along with that water which is going out, which we may not be aware. That is what I told. Just like that, while importing some of the products from other countries also, suppose what is that, some textile or some other that importing products. So along with that import, we are also getting. Unknowingly, they are exporting and we are getting some more water. So that is a national, but we are not much aware of those water transactions actually between countries. So,
and I had one doubt when we had given the figure of water footprint of about millet, it is about 2,400. And as we know that millet is a lower water requirement crop, and how, then why is that the water requirement of millet is so high than other millet?
Yes, actually it is a valid question. You know the millet cultivation, where we don't have much improved varieties of millets. When you take the average productivity of millets, you compare it with other cereals. You know the average productivity of millets compared to cereals, the productivity level is much less. The one thing is, it is mostly cultivated, not following any scientific frankly telling, all the millets we don't have the scientific package of practices for cultivation. Mostly we are using some wastelands for its cultivation without any care. Just sowing somewhere, whatever moisture is available, just and mostly it is rain fed only, no irrigation, no artificial irrigation. If rain comes, okay, the crop will come. And but that is, it is though it is neglected, it is giving you some millets. Is it not? So we cannot expect the yield level or the what is that even under rain-fed condition also. Suppose if you are getting 1000 mm of rain for a particular millet growing season, that all the water may not be available to that crop also, because since we are cultivating the millet crops under the most neglected condition, most of the water will be moving away from that field, and no fertilizer, maybe some farmyard manure at the beginning, that also very rare. So productivity level of our millets is very less compared to the cereals or any other commercial crops. That is why even though water is going, and that too from rain, what is that, the value of water footprint will be naturally more. But in rice, we are taking into account whatever water we are adding. We have some package. This much water level should be maintained all throughout the crop growing season. We have all the records for the assessment, and accordingly we will get more yield also.